the most heavily armored battleship ever built, is being dismantled by organisms smaller than a grain of dust. Not by enemy torpedoes, not by the crushing pressure of 5 kilometers of ocean, not by the slow chemistry of salt and water working through steel over decades. By life, by microscopic life that has been patiently eating iron since before the first fish swam in the Cambrian seas. And what is happening right now to the Bismarck at the bottom of the Atlantic Ocean is not just the story of one warship. It is a preview of what the planet intends to do with everything human civilization has ever built from steel. Here is the idea that changes everything. Engineering creates structures. Biology inherits them. And biology has never lost that negotiation in the entire 4 billion year history of this planet. Not once. The Bismarck was built to be unsinkable. It lasted 8 days at sea before the British fleet sent it to the bottom in May 1941. But even the engineers who built her, even the admirals who feared her, could not have imagined the real challenge she would face. Not the challenge that came from above the waterline, the one that came from below it, from a world of biological processes so ancient, so efficient, and so thorough that the concept of a permanent human structure simply does not exist within them. What exactly are those processes? And what are they telling us about every steel structure we have ever put into the ocean? That answer begins nearly 5 kilometers down, in a place where the rules of the surface world no longer apply. The wreck of the Bismarck rests at 4,791 meters below sea level, roughly 650 kilometers west of Brest, France. It was first located by oceanographer Robert Ballard in 1989, 48 years after it sank, lying upright on a volcanic slope with its hull partially buried in abyssal sediment. At that depth, pressure reaches 480 atmospheres. To understand what that means physically, imagine a fully loaded Boeing 747 sitting on every single square meter of the hull. Every centimeter of the ship's surface, at all times, is bearing that load. Temperature holds near 2 degrees Celsius, just above freezing. Sunlight has not reached that seafloor once in the entire history of Earth. There is no photosynthesis. No seasons, no storms, nothing that connects that environment to the world where the Bismarck was built. Conventional science would predict that decay should nearly stop in conditions like these. Cold temperatures, slow chemical reaction rates, low oxygen limits the oxidation that drives surface rusting. The deep ocean looks, on paper, like a near-perfect preservation environment. And for the first few decades, that is largely what it was. But here's the paradox that every expedition to the Bismarck has been forced to confront. The ship is dissolving faster than the chemistry alone can account for. Something is accelerating the process. Something that does not show up in standard corrosion models. Something that requires a completely different scientific framework to understand. That framework exists, and the implications of what it reveals reach far beyond one German battleship. Before explaining what is eating the Bismarck, it is necessary to understand something about steel that most people never consider. Steel is not a natural material. It is iron that has been forced, through enormous industrial energy, into a high-energy state that the planet did not create and does not recognize as stable. The iron ore it came from was a lower energy compound in chemical equilibrium with its environment. Refined steel is that same iron held artificially above its equilibrium state, like a compressed spring that has not yet been released. The moment steel contacts water and oxygen, thermodynamics begins pushing it back toward equilibrium. What we call rust is not damage. Rust is the universe correcting an imbalance. It is entropy reclaiming material that was borrowed from the natural order through industrial force. Every steel structure ever built begins returning to iron oxide the moment it is finished. Certain microorganisms have evolved to use exactly this thermodynamic return as a metabolic energy source. They position themselves at the interface between steel and seawater and extract the electrons moving between them. They do not corrode steel the way acid corrodes metal. They metabolize it the way a cell digests glucose. The distinction matters enormously because it means corrosion in the presence of these organisms is not a passive chemical process. It is an active biological one, regulated by living systems that respond, adapt, and self-organize. This is not biology happening alongside corrosion. This is biology driving corrosion. And understanding that distinction is the reason scientists are now looking at the Bismarck not as a relic of World War II, but as one of the most important materials science laboratories on Earth. The most visible expression of this biological process was first documented on the Titanic, which rests at 3,800 meters in the North Atlantic and has been studied more extensively than any other deep wreck in history. The hull of the Titanic is covered in formations called Rusticles. They hang from the ship like brown, fragile stalactites, some reaching half a meter in length, some clustered in formations that cover entire sections of the hull. Early researchers assumed they were inert mineral deposits, a byproduct of standard electrochemical corrosion. Then microbiologists examined them in detail, and the field changed permanently. A single rusticle contains millions of living microorganisms operating as an integrated biological community. Halomonas titanicae, first formally described as a new species in 2010, is among the most active iron-oxidizing bacteria found in these structures. Sulfate-reducing bacteria in the deeper layers consume metabolic byproducts and generate hydrogen sulfide. Biofilm-forming species build the physical scaffolding that holds the colony together and controls water flow through its interior. These are not random accumulations of cells. They are structured ecosystems, each one operating as a miniature processing facility for converting steel into dissolved ions and biological energy. The metabolic output of these communities is measurable. Scientists estimate the Titanic is losing approximately 180 kilograms of iron per day to microbially influenced corrosion across its entire hull surface. Structural engineers analyzing the rate of internal degradation project that major sections of the ship could collapse within the next 20 to 50 years, not from external pressure, but from the inside out, as biological activity hollows load-bearing members long before external collapse becomes visible. The Bismarck has the same biology working on it. The question is only how far along the process has advanced. And that question connects to something that engineers designing modern ocean infrastructure are increasingly treating as urgent. What can the rate of biological decay on a World War II battleship tell us about the long-term survival of the steel structures we are placing into the ocean right now? The Bismarck was armored with Krupp cemented steel, the finest naval armor plate available in the world at the time of her construction. The main waterline belt ran 320 millimeters thick. Deck armor in critical areas reached 80 to 120 millimeters. The face-hardened surface layer of Krupp cemented plate could deflect shells that would punch straight through the homogeneous armor used on lesser warships. British naval architects studied captured samples of this steel with something close to professional envy. It was, by every metric available in 1939, the best protective material that industrial civilization had ever produced. That metallurgical quality still has measurable effects at the bottom of the Atlantic. The Bismarck rests deeper than the Titanic, in colder water with lower ambient oxygen levels and reduced organic nutrient input. Expedition footage from visits in 2001 and subsequent years shows sections of the main hull that remain structurally recognizable. The bow is largely intact. Parts of the main gun turrets are identifiable. The anchor chains remain in place. Compared to the advanced structural deterioration visible on the Titanic, the Bismarck looks, superficially, better preserved. But established microbial communities on the Bismarck surface have reached bacterial densities of up to 10 million cells per square centimeter. At that density, the local chemistry around the biofilm is no longer determined by the surrounding ocean water. It is determined by the biology itself. The microbes are engineering their own microenvironment, regulating pH, oxygen concentration, and iron ion levels to optimize the conditions for their own metabolism. The best steel ever produced by industrial civilization is being processed by organisms that do not recognize the concept of engineering achievement. They recognize only the electrochemical gradient, and that gradient is food. One of the most counterintuitive discoveries in deep wreck science is the relationship between a ship's visible condition and its actual structural integrity. Warships are architecturally complex. They contain hundreds of internal compartments, rivet lines, armor seams, ventilation shafts, ammunition handling spaces, engine room bulkheads, and machinery voids. Each one of these structural features creates a different microenvironment. In confined spaces, water circulation slows. Oxygen gradients form across distances smaller than a millimeter. Nutrients accumulate. Sulfate-reducing bacteria, which thrive in exactly these low-oxygen, confined conditions, establish themselves inside the ship's structure itself, not just on its outer surface. Their metabolic byproduct is hydrogen sulfide. Hydrogen sulfide reacts with iron to form iron sulfide compounds that are structurally weaker than the original steel. Load-bearing frames can be chemically transformed from the inside, their cross-sectional strength reduced by 40 to 60%, while external surface appearance remains largely unchanged in ROV camera footage. The ship looks intact. It is not. This internal failure mechanism is precisely why deep ocean engineers have stopped trusting visual surveys of old steel structures as a reliable guide to remaining structural life. The same principle applies to modern infrastructure. Offshore platform legs, submarine pipeline supports, and deep-sea mooring systems all create the same kinds of confined microenvironments that sulfate-reducing bacteria favor. The science developed to understand the Bismarck's internal decay is now being applied directly to the inspection and maintenance protocols for oil and gas platforms operating in the North Sea and the Gulf of Mexico. The battleship's death is teaching engineers how to keep modern structures alive. That feedback loop between a World War II wreck and 21st century ocean engineering is one of the most unexpected scientific legacies of the age of battleships. Here is where the story of a single German battleship becomes a story about how the planet manages the materials of technological civilization. Iron is a limiting nutrient across enormous stretches of the open ocean. In large areas of the South Atlantic, the Southern Ocean, and the equatorial Pacific, dissolved iron concentrations fall so low that phytoplankton cannot grow. Without phytoplankton, the entire marine food web from zooplankton to fish to whales is starved at its foundation. These iron-limited regions are among the least biologically productive areas on the planet, covering hundreds of millions of square kilometers of ocean surface. A large steel wreck dissolving at the abyssal seafloor releases iron into the deep circulation system over centuries. Upwelling currents can carry that dissolved iron toward the surface, where it becomes bioavailable to phytoplankton. A single battleship, converted by biology into a slow-release iron source, can influence ocean chemistry across a radius that dwarfs the ship's original physical dimensions. The Bismarck is not simply decaying. It is being converted from a machine into a nutrient delivery system, into a component of the global iron cycle that regulates biological productivity across millions of square kilometers of ocean. At the same time, the physical structure of the wreck has become an artificial reef in an environment that is otherwise a nearly featureless abyssal plain. Cold-water corals, sponges, anemones, and crustaceans have colonized the hull, the gun turrets, and the surrounding debris field. Multiple species discovered on the Bismarck were previously unknown to science. The ship that was built to project military power has become a biodiversity hotspot in one of the most biologically sparse environments on Earth. The ocean does not record what things were built to do. It records only what materials they contain and what ecological function they can serve. And by both of those measures, the Bismarck has already become something its builders never imagined. Not a weapon, a habitat, and eventually, geology. The models scientists use to project deep wreck lifespans draw on rusticle growth rates, measured microbial iron consumption, and structural engineering analysis of hull degradation across multiple deep wrecks. The resulting timelines reframe what human permanence actually means. The Titanic has already been on the seafloor for 113 years. Current structural analysis suggests it may retain recognizable form for another 20 to 50 years before biological and physical collapse removes its identity as a human structure. The Bismarck, resting deeper and in colder water, is projected to persist somewhat longer. Conservative estimates suggest 100 to 200 additional years before the main hull loses structural coherence entirely. At the outer edge of optimistic projections, possibly 300 years, consider what that means in historical context. The pyramids of Giza were built approximately 4,500 years ago and remain standing. The Pantheon in Rome has stood for nearly 2,000 years. Medieval stone cathedrals built in the 12th century will outlast the Bismarck by millennia. The most advanced engineering material of the 20th century, the material that built the industrial world and the navies that fought its largest war, will vanish from the seafloor faster than almost any stone structure built by pre-industrial civilizations. Steel belongs to the planet's iron cycle. The planet lends it out temporarily in the form of ore, accepts it back briefly in its refined industrial form, and then reclaims it through biology and chemistry on a timeline that has nothing to do with the significance human beings assign to what the steel was used to build. The Bismarck was one of the most historically significant objects ever placed in an ocean. The ocean does not have a category for historical significance. It has a category for iron, and the iron is already on its way back. Modern civilization has placed thousands of steel structures into the world's oceans. Offshore oil and gas platforms operating in the North Sea have been producing since the 1970s. Deep-sea mining systems are being designed to operate for decades on abyssal seafloors at depths comparable to the Bismarck. Submarine fiber optic cables, carrying over 95% of international internet traffic, are armored in steel wire and laid directly on seafloor sediment. Decommissioned naval vessels, pipeline networks, and mooring systems extend across the continental shelves of every ocean on Earth. Every single one of these structures is subject to the same microbially influenced corrosion now processing the Bismarck. The organisms do not distinguish between a 1,941 battleship and a 2010 platform leg. They distinguish between an iron-containing surface and seawater. That is the only chemistry they require to begin their work. The materials science discipline that emerged from studying deep wreck deterioration is now a recognized specialty in offshore engineering. Understanding how Halomonas titanicae and sulfate-reducing bacterial consortia colonize steel surfaces, regulate local electrochemistry, and drive corrosion far beyond what abiotic models predict is considered essential knowledge for designing structures that are expected to remain intact for 25, 50, or 100 years in the deep ocean. The inspection intervals, cathodic protection systems, and protective coating specifications for modern offshore infrastructure have all been revised in response to what scientists learned from wrecks like the Titanic and the Bismarck. The warship, built to project power, is, in its dissolution, protecting the infrastructure of the civilization that came after it. That is not a metaphor. It is the actual pathway by which knowledge flows from deep ocean microbiology into engineering standards that govern real structures holding up real energy systems right now. Technology dominates environments briefly. Biology dominates them permanently. And the most useful thing a battleship can do, it turns out, is teach the next generation of engineers how to lose to biology more slowly. Today, the Bismarck rests in total darkness at 4,791 meters, in a silence and cold that no human being will ever directly experience. Its main gun turrets, which once fired 800-kilogram armor-piercing shells across 30 kilometers of open North Atlantic, now host cold-water coral colonies. Its 320mm Krupp armor belt, engineered specifically to stop the largest naval artillery of its era, is being dissolved atom by organisms that have no awareness of what it was designed to do. The most powerful warship of its generation is being processed by the most ancient biological system on Earth. And in that process, something profound becomes visible. Human engineering is not a permanent addition to the planet. It is a temporary transformation of planetary materials. We borrow iron from the Earth's crust, force it into shapes that serve our purposes for decades or centuries, and then biology reclaims it through processes that were running hundreds of millions of years before we arrived and will continue hundreds of millions of years after we are gone. The deep ocean does not destroy our machines. It decides what part of them can belong to the long material cycle of a living planet. The Bismarck will be gone before the civilization that built it has been forgotten. The coral growing on its turrets will outlast any documentation of the battle that sent it to the bottom. The iron atoms currently leaving its hull will eventually become part of organisms that have no evolutionary relationship to anything alive today. That is not a tragedy. That is the actual timescale on which the planet operates. And it is a timescale against which the concept of a permanent human structure is, quite simply, a misunderstanding of what permanence means. We build in steel, the planet collects in biology, and the collection, as the Bismarck makes clear, is already well underway. If stories like this fascinate you, where ocean science, deep time, and engineering reality converge to reveal what actually happens after history sinks beneath the surface, subscribe to Sunken Realms Deep, because far below the waterline, the ocean is still answering a question most of us never think to ask. Not how ships sink, but what the planet does with the civilization that built them.